Welcome back. In this video, we're going to go over some examples of what parameterized vector valued functions look like. Just to give an idea of generally what these look like, it's when we have a vector r of t, which is described by each of its components using functions of t. So each component in the vector is a function of t, a single input. So an example is something that we've already seen actually. R of t equals this vector here, 2 plus 3t, 3 minus 6t, and then negative 7 plus 6t. That would just be an example here of what a parameterized vector valued function is. So just the idea is we plug in a single value t, and then because each one of these has kind of like a function in the components, we're able to get an entire vector out of it. And this is actually the same as the line, which we've already learned how to work with parameterizations of. R of t equals 2, 3, negative 7 plus t times 3, negative 6, 6. So we can kind of split that up there into that parameterized line form that we're familiar with already. If we want to talk about the domain of a parameterized vector valued function, it's the same idea as it is for a regular function. It's the set of all possible inputs t. And one thing that I do want to point out, though, is that there are now 3 different aspects that we have to consider when we're looking at this domain, and you want to make sure that t works in each component. So quick example here, if we find the domain of r of t is equal to, say, square root t plus 1, square root of t, and then 3t, we can kind of think about each of these components separately. This guy right here would have a domain of t greater than negative 1, because we need the inside of this guy to be greater than or equal to 0. The inside of this has to be t greater than or equal to 0, and then this t can be any real number. So of these 3, this is our most restrictive requirement, t greater than or equal to 0. If it satisfies this requirement, then it will also wind up satisfying either of these other 2. So then our domain in this case is just that t is greater than or equal to 0, since that's the one restriction that works for all the components. Now, some really common examples of working with parameterizations of these functions is to find parameterizations for a circle. So I wanted to work through a couple of examples with that. Okay. So generally speaking, our goal when we're trying to parameterize a given function is to turn whatever equation we've been given into that has the x and the y's, we want it to become something that looks a little bit more like a vector with the x and the y components, okay? So we want to figure out how to convert the standard equation into something that looks a little bit more like that still describes the x and the y positions. And when we're working with circles, the big idea or if we even actually want to look at even ellipses, though I won't cover that in this video. we are going to use the equation r squared cosine squared of t plus r squared sine squared of t is equal to r squared. So this comes just from the identity that cosine squared plus sine squared is equal to 1, and then we've multiplied r squared all the way through that. We can think about this guy right here corresponding to our x component and this guy right here corresponding to our y component, and we'll work through some specific examples that show how those wind up being related. So let's jump right in. In this example, we have an equation for a circle x minus 5 squared plus y plus 3 squared is equal to 4. So in this case, we have a circle of radius 2, and the center is at 5, -3. And so in this case, all we have to do here is we want r squared cosine squared plus r squared sine squared to be equal to r squared. So to be able to do that, we're just going to say that this guy right here is going to be that 4 cosine squared t, and then this guy right here is going to be 4 sine squared t. And then this plus this is equal to 4, using that same identity that we did earlier. So our goal then is to be able to figure out how to make this correspond to the x and the y components, though, because this x and this y still correspond directly to that r of t is equal to xy. So need to arrange into r of t equals that x and the y component there, like so. So looking at this piece here, we have that if we get rid of the squares on both of these two terms, x minus 5 has to be equal to 2 cosine t. And then we can solve for x, so we know what to put in here. X has to be equal to 2 cosine t plus 5. And then similarly, we have y plus 3 is equal to 2 sine of t. So then y has to be equal to 2 sine of t minus 3. So then these two things right here are going to be what goes in for our x and our y components. So we get r of t is equal to 2 cosine t plus 5, and then 2 sine t minus 3 for that y component there. And that's pretty much all there is to this example, to being able to work with circles. The strategy for working with an ellipse is actually nearly identical. So let's do an example that's a little bit more involved using this circle. So we're going to find the parameterization of a circle that has the center 1, 3, -2, and has radius equal to 5. And we have one more piece of information about this circle, that it is parallel to the xy plane. Okay. So generally speaking, when we're working with these parameterized functions, our goal is going to be that r of t is equal to some expression for x, some expression for y, and then some expression for that z component there as well. So I'm actually going to start by approaching this z component, because if we can get this, then it simplifies down to just having to solve for these two guys right here. And the reason I know that I have this kind of information here is actually based off of this parallel to the xy plane thing. So if we kind of sketch a picture of this, like so, and I have a circle that maybe looks kind of like that, and suppose it's hovering above the xy plane, like so. If it is parallel to the xy plane, then z, whatever value it's hovering at, z has to be constant everywhere on this circle. So that means that z at the center is the same as, say, z over here, or anywhere else on the circle. So since we know that we have the center at 1, 3, -2, we must have that z is equal to -2 everywhere. So all we have to do then, now that we've got this z component here figured out, we just have to deduce x and y. And since now we've simplified it down to a problem that only involves x and y, since z is always the same, we can set up our equation for a circle. And that's going to be that we have x minus 1 squared plus y minus 3 squared is equal to that 5 squared, because that's our radius. And this piece right here is 5 squared cosine squared t. And then this piece right here is 5 squared sine squared t. And so at this point now, all we have to do is just go through the same process that we did on our last example, which means just kind of rearranging a little bit, and we get that x is equal to 5 cosine t plus 1, and y is equal to 5 sine of t plus 3. So putting all of this information together, our parameterization in this example winds up being r of t is equal to 5 cosine of t plus 1, 5 sine of t plus 3, and then finally for our z component, it's always equal to -2, so that's what we put in right there for our last component. So this is pretty much it for this video. In our next video, we will cover some applications of calculus to these types of functions. So I'll see you next time.